In this video, we are going to continue from where we started last time. So last time we talked about the relation between non-backtracking random walks and the Chebyshev polynomials, and we had this equation that on one side had a kind of a spectral flavor. It was some summation of Chebyshev polynomials applied to the eigenvalues of the Cayley graph we want to consider. This was a general Cayley graph then, and now it's going to be in particular our graph XPQ or YPQ, isomorphic. And on the other side, we had this summation of how many non-backtracking walks do you have of certain lengths. So what we're going to do now as a step towards proving that LPS is an expander, but actually it's also a step for proving that LPS is a Ramanujan graph. We will see that the split occurs at the end of this lecture. So everything we did so far actually is used to prove that this is a Ramanujan graph also. Anyhow, we are going to interpret the left-hand side as algebraically in a sense. So we are going to relate it with the quaternions that were used to build the graph. Okay. Right, so recall that last time we actually proved this thing. Oh, well, I didn't mean to do that. Last time we proved this thing. That's what I just talked about at the intro, right? The left side is combinatorial, counting non-backtracking random walks, generally on the graph that you are considering. And the right-hand side is spectral. It has some relation. It is dependent by, it depends on the eigenvalues via this Chebyshev polynomial. Anyhow, but that was a general setting. And in our case, we are going to consider XPQ. So we are going to consider P, which is 1 modulo 4. If you remember, when it's 3 modulo 4, we are going to look at a bipartite graph. So it requires some care. So I'm just going to consider the non-bipartite case. And we already used a couple of times that P is a square modulo Q. So we are going to hang on to that assumption. N is the number of vertices of XPQ. I mean, we know exactly what is the number in terms of P and Q, but let's just call it N. And the eigenvalues are denoted by M0 down to Mn minus 1, where because the graph is P plus 1 regular, M0 is P plus 1. Because it is connected, you have a strict inequality here. And by the way, because it's non-bipartite, this is strictly larger than minus P minus 1, P plus 1. Okay. And yeah, so FM counts the number of non-backtracking walks of length n, m, starting and ending at 1. I'm going to assume in a Cayley graph, it's the case that the graph is vertex transitive, so it doesn't really matter from which vertex you start. If you remember, this is the simplification of the more general formula for vertex transitive graphs, where you don't have the dependence of V here and you don't sum over V. That's why you have the factor of n here, because we normalized. Anyhow, so that's what we have. And now what we are going to do, the first part of this lecture, is we are going to consider this combinatorial side and make it algebraic. Not analytic, not spectral, but algebraic in terms of quaternions. So we're going to interpret the left-hand side as something else. And to do so, let's consider the following function, q of x0 up to x3. So it's just x0 squared plus q squared times the sum of the squares of the remaining x's. Okay, and let's consider this number, sq of p to the m, as how many 4 tuples of integers you have, such that when you plug this 4 tuple to q, you get p to the m. So here you'll get p to the m. And also x0 is odd, and the remaining x's are even. This sounds a bit arbitrary, but okay. And we actually, I mean, these conditions, you saw them before. They came from these definitions of lambda or lambda prime and so forth. But I want to clean this a little bit up. So know that because x0 is odd, or actually because these are even, you can pull out a factor of 2 And you don't need to require them to be even, but you need a factor of 4 here, because you pull out a factor of 2 for each of them, and they're squared. So what I'm saying is that if you're going to consider this Q prime, which is similar to the Q above, but it just has this coefficient of 4 before the Q squared, then SQ of P or to the M, sorry, there is a typo here, is the number of integral representations of P to the M by the quadratic form Q prime. Right, so I mean, these conditions are met, kind of immediately met, because of this factor of 4 that you have there. Okay, so all you need to require is that the norm, like there is no quaternion yet, but the 4 tuple. Okay, so anyhow, SQ of P to the M is the number of integral representation of P to the M by this Q prime. That's what I'm saying. And the reason we care about this SQ is that it turns out that the left-hand side, let me go back. So this was the left-hand side. So it appears here, well, with this factor of 2, but this left-hand side is precisely SQ of P to the M over 2. So the number of non-backtracking random walks, well, from lengths, 0 up to M, jumping in steps of 2, is because of the graph structure. I mean, we're going to prove that that's the technical part of this talk, is exactly how many solutions do you have, how many elements do you have in this SQ of P to the M set. Okay, so not quaternion yet, but you see the quaternion kind of coming in, and yeah, this is certainly more algebraic or number theoretic than combinatoric. So the proof is a bit kind of somewhat technical. And first of all, let's remind ourselves what Y is. And even before that, I think, let's start with that. This should have come before. So recall that lambda prime is the set of all integral quaternions such that either the free coefficient is odd and the rest are even, or the free coefficient is even and the rest are odd. We are going to consider the case of P equals 1 modulo 4, and so this is the only case that we are going to have anyhow, so this OR is kind of redundant. But generally speaking, it was defined like that, just to support P equals 3 modulo 4, and that the norm of the quaternion is a power of P. Right? We had this set, and on that set, we defined a weird equivalence relation. It was weird, but it wasn't weird if you remember the kind of unique factorization that we had for quaternions. Anyhow, so alpha is equivalent to beta if alpha and beta are plus minus 1 of each other, and maybe there is some powers of P's that require them to be equal. And you can show that this is an equivalence relation. We show that or say that maybe, and we denote by Q the quotient map, the projection that takes every element in lambda prime and produces an element in the quotient, which we denoted as lambda. Okay, so that was part of the definition of Y, not X actually. Sorry, maybe I should go one more. Yeah. And with this, recall that Y was defined as follows. So let me kind of zoom in here. So yeah, so this part of the picture is actually X. So you can ignore that. This is the way we define X, this is the way we define Y, and it's all the same, isomorphic to each other. So, but let me still have it. So what we did was this, so lambda prime sits here, and we show that, as we said, it's obvious almost, that SP is a subset of lambda prime. So the first thing we did in order to define the graph Y was to use our projection map that we just saw. It takes an alpha to its class, with respect to this weird equivalence relation. So you go to lambda like that, and then from lambda, you use pi q, which is just this, tau q descended to the quotients. So tau q was just, take modulo q, and we show that this map is well defined when you go down to the quotients. Okay, so we said that this diagram commutes and also this one. So what I'm saying is that the graph y, what kind of sits here, the way you construct it is, so the generators, you're going to take SP, apply Q to them, and then apply pi Q to them, and that will give you TPQ, what we call TPQ. So this is just, you apply Q, you apply Q, and afterwards you apply pi small q to SP. And we show that, this preserves the size, so you still are left with size p plus 1 set. So TPQ sits here, and so that these are the generators, but the actual group that you're working with is the image of pi q of lambda. So you look at lambda, you look at the image of pi q, and right, so it's some subset here. Confused for a second. Yes, it's some subset here, and I'm identifying the image with, according to the first isomorphism theorem, with lambda modulo the kernel, which was defined to be, we wrote it as lambda q. Afterwards, we also had the little claim that explains exactly more explicitly what's in the kernel, but that's how we do it. So yeah, so this is the group that the Cayley graph is based on. This is the vertices, these are the vertices, and these are the generators. Okay, so anyhow, with this, let me maybe clean it a little bit. Yeah, it's kind of a lot. So yeah, so with this, let's start the proof. So first of all, we're going to actually show that this holds for y and not for x. But these are isomorphic graphs, so the number of non-backtracking random walks and so forth are the same. So let's say that we have a length L. Let's start. What we're going to do initially is not considering the sum at all. We're just going to somehow interpret a particular sum in here algebraically, okay? As the number of some reduced words somewhere. So we will see. So generally speaking, let's say that you are taking a path, a non-backtracking path in y. x0, you can start at 1 because this is a vertex transitive graph. It's a Cayley graph, so you can start at 1. It's all the same in terms of numbers. So x0 and xl are the same, and this is vertex number 1, and then you have x1 up to xl minus 1, and then xl. And this is a non-backtracking path in y. Now, because y is a Cayley graph, it means that you have this set of generators, T1 up to TL in TPQ, such that every xi is the product starting from Ti ending at Ti, T1 up to Ti. So Ti kind of sits here, also the xi sits here. And the Ti's, as I said, they are application of pi q following by application of capital Q. So you can write every Ti as pi q applied to the class of an alpha I, where alpha I sits here in SP. Right, and these are unique. We talked about it. So the alpha I is determined by the Ti. Okay, so far the picture is this. Actually, I wrote it here. So the xi's are here, the Ti's that gives you the xi's by product are here. These are the generators. This is the way xi is being generated. And Ti is a capital Q applied to alpha I followed by pi q. Okay. Now, so what I'm claiming is that these guys, if you take the product alpha 1, the class alpha 1, up to the class alpha L. This is a reduced word of length L in lambda. And it's reduced because it comes from, or it is lifted from a non-backtracking walk. Right? A non-backtracking walk means you don't go back, you don't kind of regret immediately, which means that there are no two consecutive things that collapse to one, to identity, which is exactly the definition of a reduced word when you don't have such a thing. Okay, so non-backtracking corresponds to reduced words, and that's why we that's one reason why we like non-backtracking walks. Okay, and now note on top of that PyQ, when you apply it to the product, right? So you should look here. When you apply PyQ to the product, you get the product of the TIs, right? It's an isomorphism or a homomorphism. So you can detect the product of the TIs, which is from T1 up to TL, which is just XL, which is 1, because you started and ended at 1. And 1 is in the kernel of PyQ. It's in ZK, right? I mean, you need to remember what ZQ is, but it is. It's essentially isomorphic to FQ star, and 1 is in FQ star. So this means that this product is in lambda Q. It's in the kernel of the map PyQ. So what we just showed is that if you take a non-backtracking path in Y of length L, starting and ending at the same vertex, you get, and the number of those is FL by definition, then you get a reduced word of length L in lambda Q. And then if you think about it, this is reversible. So actually FL is the number of reduced words of length L in lambda Q. We just interpreted things. We didn't there was no implied. It was all kind of just changing the types of things. So if you think about it, FL, I mean, what we did in one direction, but it's the same. FL is the number of reduced words of length L in lambda Q. So that's what I said about, in order to prove that, we first understand this combinatorial thing as the number of reduced words somewhere, in lambda Q. Okay, so that's the recap that we already did. And now let's recall, as I mentioned before, that we have an explicit description of lambda Q. So that's something that we proved some time ago. This is the set of classes of integral quaternions coming from lambda prime. So the set of classes in lambda such that Q divides all the non-free coefficients, okay, A1, A2, and A3. And recall we want to prove this thing. So let's consider first a 4-tuple that contributes to SQ of P to the M. Right, SQ of P to the M was, by definition, was this thing. How many 4-tuples do you have such that Q of that 4-tuple is P to the M and Q0 is odd and the rest are even. And so let's take such a 4-tuple of integers. So we know that Q of that 4-tuple is P to the M, Q0 is odd, and the remaining are even. From that, let's construct a quaternion which looks like as follows. So you have x0 plus q, and then you use the x1, x2, and x3 as coefficients of I, j, and k. Okay, so first of all, note that this is in lambda prime, because in order to be in lambda prime, this is here, your norm has to be a power of p to the m is okay, and alpha should be 1 modulo 2, and the rest should be even. And we started from a 4-tuple that has these properties, and multiplying by q doesn't change anything. So we know that alpha that we constructed from the 4-tuple is in lambda prime, and because of this explicit form of lambda q, we know that the class of alpha is in lambda q. right? Because we made sure that Q will divide all the non-free coefficients, but just put in the Q here. So that's fine. And again, as before, this is actually reversible. So if you have any quaternions that x0 is odd and the remaining are even, and it has a norm which is a power of p, and its class sits in lambda q. So what we just did was to show that every solution that contributes to SQ to P to the M gives you a quaternion alpha in lambda prime, whose norm is P to the M, particularly P to the M, and Q divides all the non-free coefficients. And what I'm claiming is that actually there is an equality, because if you start from the right side, or if you just see everything is reversible, if you take any alpha in lambda prime, whose norm is P to the M, and Q satisfies this, it divides the non-free coefficients, then you can form a four tuple that contributes to SQ of P to the M. Yeah, just by construction. So we did one more step now. We interpreted SQ of P to the M as this kind of quaternion language, right? Which is good, because the thing we did before, the lemma, I mean, the first part of the lemma, we are still in the proof dilemma, but the first part of the lemma was to write each of these summons as in terms of quaternions, and now we just did it to the left-hand side. So now everything is in terms of quaternions, and we just have to look at it and see why we count the same thing. There is no solution to equations and non-backtracking random walks. It's all now of the same type. So to recap what we proved, I mean, we want to prove this. And what we showed just now is that SQ of P to the M can be expressed as, how many quaternions do you have, integral quaternions, whose norm is P to the M, and Q divides the non-free coefficients. So that's the left-hand side. And on the right-hand side, we have, for each summand, the number of reduced words of length m minus 2r, FL generally, but here L is m minus 2r, in lambda that belong to lambda q. Okay? So you just have to look at these two clouds and make sure that they're the same. And that goes through the unique factorization. So let's see that. So let's take alpha in this on the left-hand side. So a norm P to the M, and Q divides the non-free coefficients. So, generally, because of unique factorization, which kind of leads the entire discussion here, alpha can be written uniquely as plus minus P to some L times a word W of this thing, M minus 12. And this is a reduced word in SP of length M minus 12. Okay? So the class of alpha is reduced in lambda and belongs to lambda q. Right? It belongs to lambda q because we know that and that. And it's reduced in lambda because when you look at lambda, the P to the L and the plus minus 1 goes away, and you are left with a reduced word in lambda prime, which induces a reduced word in lambda. Okay, so if you take alpha in the left-hand side, you get something on the right-hand side. And the length of that something, I mean, here you have a sum. So if you take an alpha here, a solution here, you'll get a contribution to the right-hand side, and in particular to the summand, with index R is like how many p's you have that divides alpha. Okay, and this is again reversible. So if W is a reduced word of length m minus 12 in lambda q, then you can look at this alpha. Okay, it will be on the left-hand side, and it will produce two alphas as above. There is I forgot to say, there is this 2 factorial because of the plus minus 1. Each of them will be. Good, so that's it. That's the proof of this lemma. It's quite technical. So again, what we just proved is that the combinatorial side that we had, which was equal to something spectral, can be written algebraically in terms of quaternions. So with this, let's consider the following subset of the complex plane. We call it theta p. So theta p is the following. So this is this picture. So this is the complex plane. And what you're doing is you're looking at the union of these three segments. You start from I ln square root of p down to 0. And then you go right to pi. And then you go up to pi plus I ln square root of p. Okay. So you'll see why we care about this thing in a second, but let's consider the map from this theta p that takes z to t square root of p times cosine of z. And what I claim, and we'll talk about it, is that this is a bijection actually between theta p and the interval between the real interval between minus p plus 1 to p plus 1. And not only that, this bit, this segment, is bijected with that. This is actually not the right scale. This is much smaller than that, but never mind. So this thing is bijected with that. This part, this bit is bijected with that. And interestingly, the segment, the real part of theta p, the segment 0p, is bijected with this bit, which is precisely kind of the Ramanujan segment. There should be nothing there. So right, so this is minus 2 square root of p, where the degree is p plus 1, so it's 2 square root d minus 1, and 2 square root of d minus 1, plus minus of 2 square root of d minus 1. So let's see that for a second before moving on. Make sure we understand this. So let's see. So let's start with this segment first. So I'm going to use the kind of this identity. We don't have issues with like complex analysis kind of issues of branching, so don't worry about that. So let's consider cosine z to be, recall that cosine of z is e to the iz plus e to the minus iz over 2. So if you're going to consider a general point on this line, so it's some I ln y, right? Here y is square root of p, and here y is 1, so that ln 1 would be 0. So you start at square p and descend down to 1 in terms of y. So anyhow, a point here, which is I times ln of y, what is it mapped to? So let's see. So it's 2 square root of, I'm looking at this bijection, this map. So it's 2 square root of p times cosine of I ln y. And I ln y, you can use the cosine identity here, right? So you get too many stuff going on here. So you get square root of p, and these two cancel that too, so you don't see it. And then you have e to the I times I ln y. This is I ln y, plus e to the minus I of the same thing, I ln y. And if you look at it for a second, this is 1 over y, because it's e to the minus ln y. And this is y. So generally speaking, this is how it behaves on this particular segment of theta p. So in particular, at the edges, you can see that when y is square root of p in this red dot, you get p plus 1, because you have a square root of p. Now I'm plugging y as a square root of p. So 1 over square root of p plus square root of p, which is, you form, okay, so it's square root of p, 1 plus p, like square root of p squared, over square root of p, and it cancels, and you get this p plus 1. Right? So this red dot goes to p p plus 1 as promised. So this is why you have a red dot here and a red dot here. And when you plug y equals 1 and you go all the way down here, well, when you plug 1 here, you get just 2, right? So that's the 2 square root of p. Now, for this line segment, it's the same thing because 2 square root of p cosine of now this segment is like pi plus I ln y, where y goes from square root of p to 1. But the pi just adds like a minus to the cosine. So the previous calculation that we did reflects around 0. So you get that. So this is mapped here. Right, so you see this pink dot is that pink dot. And this part is mapped here. And the middle part, in the middle part, everything is real. And when you plug something between, so that's kind of obvious. When you plug something between 0 to pi in cosine, you get something between 1 and minus 1. So that's where you get the square root of p and the minus square root of p. Right, so as you go here, like that, you go here like that. Okay. So again, we have this theta p part of the complex plane, and we do a change of variables. Z goes to 2 square root of p cosine z. The cosines is not it shouldn't surprise you because we are going to use the Chebyshev polynomials. So that it should have come at some point, you know, the gun that appears in the first act and so forth. So z goes to 2 square root of p cosine z, maps this segment to a really where like the eigenvalues live, right? Like they live between minus p plus 1 to p plus 1, and you want to make sure they won't live here. But more concretely, I think something kind of blocks the view here. So if you look here, then I'm just reminding you that SQ of p to them, well, you know, it's this expression. We'll see it again in a second. That's okay. Right, so now let's denote by theta j the pre-image of mu j under this map. Okay, and anyhow, maybe this is a mu j, so let's consider the pre-image. This is a bijection, so let's consider the pre-image and we'll call it theta j. So maybe it's here, something. Okay, it's between the red and the pink. And we know, for example, that theta 0 is I ln square root of p. Right, theta 0 is this thing. Because this is mapped to p plus 1, which is mu 0. Right? And because, by the way, the graph is not bipartite, we know that theta n minus 1 is not this thing. Because the graph is bipartite if and only if the spectrum is symmetric around 0, which would implies that that's not trivial actually, that the least eigenvalue is minus p plus 1. So we have this, and by the definition of the Chebyshev polynomial UM, that's what I started to do before. When I move things around, we know this, right? We know that SQ of p to the m is this thing. But I want to express this in terms of not the mu's, but the thetas. So recall that UM has this property, right? UM of cosine theta, well, it's defined to be sine of m plus 1 theta divided by sin theta. So I'm just kind of plugging it here instead of the UM of mu j over 2 square root of pi, 2 square root of p, and I'm using the fact that cosine of theta j is mu j over 2 square root of p. Okay? So we have, in terms of the theta j's, we can write the SQ of p to them in the sum like that. So that's what's written here. And now the point is that in order to prove that the XPQ graph is Ramanujan, we must prove that except for theta 0, which sits here, all of the remaining thetas sit here. Namely, they are real. Okay, so I mean, because these are precisely those that will sit, that will have a bound of 2 square root of p. Right, that's kind of weird, right? So we had this problem, combinatorial problem of trying to prove Homogeneous and using well, somewhat convoluted route. It boils down to the question of proving that some function, the roots of some, or those theta j's, except for one, have only are all real. There is no complex solution. And so this is where we split our journey. So you would want to prove it's Ramanujan, and therefore you want to prove that all the theta j's sit here. They're all real. And you can do that, and that's deep and heavy and complicated. And I'll maybe add a video about the general idea behind it, but it's too much to do in one course. But what we will do, so following again this really great exposition by Davidov, Samek, and Valette, is we're just going to bound the imaginary part of all of those theta j's and show that a bound translates to some expansion, bound on expansion. So if they were real, you will get Ramanujan, and if maybe they are bounded, so I mean that's kind of obvious. If they are bounded, then maybe they are here, and that will translate to not being too far from this interval. And we are going to bound it in terms of P alone, not Q. So that will give you like honest to God expander, but not a Ramanujan. Okay, so next up, I think I should do like so there is one more video, but I really think we need to do some Cayley graph reminder, because we are going to look at SL2P, and there is we proved that all the irreducible, I mean the seminar we proved that all the irreducible representation have large size, except for the trivial one, and it turns out that that will be the machinery of the bound, the actual bound also, the Ramanujan bound. And you do need to relate this representation and with the eigenspaces of eigenvalues of Cayley graphs, and I think it's worth like looking at it, slowly. Okay, so we have like two more videos and maybe a third one about how you actually get proof of Ramanujan. So next up is more about Cayley graphs and the relation with representations. Then we are going to complete the proof that this is an expander, and that's the end of the course really. But then maybe, not sure, I'll add this what's missing in order to prove that this is Ramanujan.